And let's go ahead and quickly do that. It's asking us to calculate the solubility of silver chloride in grams per liter to 6.5 times 10 to the minus 3 molar silver nitrate. All right, so how will we do this problem here? All right, so silver chloride is AgCl. Okay, this is a solid that's in an equilibrium with Ag plus and Cl minus. All right, so some of it will go this way, but remember this is not in water. This is in 0.0065 molar silver nitrate. So if you remember from Chem 1, nitrate is NO3 minus. If you remember from Chem 1, nitrate is NO3 minus, so this becomes AgNO3. Okay, but all nitrates are soluble, so this is Ag plus and NO3 minus. So we have a common ion here. So what is our common ion? So some of this will go back. We'll call this plus S. Okay, we'll call this chloride ion plus S. Okay, but there's another source of Ag plus. What is that other source of Ag plus? Okay, it's from this. Okay, so we're going to call Ag plus the common ion. So this becomes S plus 0.0065. Alright, so we'll plug that in to our KSP. D plus Cl minus. So the KSP for AgCl, I'll give you that on the exam, and that is 1.6 times 10 to the minus 10. So that's a constant you'll get on the test. So this is going to be S plus 0.0065. Okay, and this is going to be S. And then we're going to assume S is small. So this is what you're going to do on the exam. So that means S plus 0.0065 is about 0.0065. Okay, so there's two sources of Ag plus. One of them is this reaction going this way, and the other one is coming from the solvent, which contains the common ion Ag plus. NO3 minus is what we call the spectator ion. It's not involved in this reaction. So when we make that assumption, 1.6 times 10 to the minus 10 equals 0.0065 times S. So S is going to be 1.6 times 10 to the minus 10 divided by 0.0065. And this is going to equal to, I went ahead and did that, 2.5 times 10 to the minus 8 big M. Okay. All right, so the solubility of Ag plus is going to be this, S plus 0.0065. Okay, solubility S is 2.5 times 10 to the minus 8 plus 0.0065, and that is about 0.0065. So 0.0065 plus 2.5 times 10 to the minus 8. 10 to the minus 8 is like really, really, really small, plus 0.0065, so this is going to be about 0.0065. Okay, because of the common ion. All right, and then the solubility of the Cl minus, okay, which is this one here. That's just going to be S. We calculated S to be 2.5 times 10 to the minus 8 molar. So this is your answer. Now, if you want it in grams per liter, okay, as per this problem, you're going to multiply it by the molecular weight. Okay, so we're going to use this number here for the S solubility because this is from the common ion silver nitrate. So we will go 2.5 times 10 to the minus 8 molar AgCl. Okay, because it's 1 to 1. One of this, sorry, it's 1 to 1. One of this to one of that. Okay, that is equal to 2.5 times 10 to the minus 8 moles over liter, because big M is moles over liter. And 1 mole of AgCl is how many grams? Chlorine is 35.45. Ag is about, what is Ag here? 107.87, you're right. Thank you. So if you add those two up, we'll get the molecular weight of AgCl. We just want it in grams per liter. So on the exam, I won't have you do that. We'll just go with our solubility in moles over a liter. $143.32 grams. And then this will be our final answer. In grams per liter, it's about 3.6 times 10 to the minus 6 grams over a liter. Okay. 3.6 times 10 to the minus 6 grams per liter. So the reason why I converted it to grams per liter is because it asks us to, but on the exam, I'll just have you do moles over liter. So, okay. But just realize solubility can also be in grams over liter as well. Okay. Solubility S. All right, this is our last set here, and that is the pH and solubility. Right, so, like we said, the common ion decreases solubility, decreases it. Okay, more will go this way. All right, one more sparingly soluble solid, and that is magnesium hydroxide. But magnesium hydroxide actually goes into magnesium ion and 2OH minus. It is sparingly soluble, and it has a KSP of whatever that value is. So one way you could actually increase the amount of solid, let's say you want to make more magnesium hydroxide solid, what can you do? You can add more base. Okay, so if you increase the pH, that is make it more basic, you make more solid. Okay. Now, so if you add OH minus, let's say you work in a company and you want to make more of this solid, just increase the pH, add more base. Okay. You'll make more solid. Right, what happens if you add H plus? Or in other words, lower the pH? What happens if you lower the pH? What will the H plus do? Okay, it will react and neutralize with the OH minus, giving you water. Okay, this is called neutralization. H plus plus OH minus gives you water. So in essence, when you add acid, lower the pH, it removes OH minus, giving you water. So according to Le Chatelier's principle, the equilibrium will react to this disturbance by moving to the right. Okay, that is moving towards magnesium ions and the OH minus ions that were left behind because we added acid. So let's say if you, in a situation where you don't want to make magnesium hydroxide, all you got to do is lower the pH. Okay, so in essence what this is saying is that you can lower the pH and dissolve the solid. You can increase the pH and make more solid, because the H plus neutralizes the OH minus. So, yep. So it's a KSP that gives you base, and then add more base. This is Le Chatelier's, you make more solid. Add acid, H plus, to neutralize the base, to give you water. You remove the OH minus, the equilibrium will shift this way, so you're dissolving the solid. All right, so how pH is related to solubility. So in this case, if you lower the pH, you increase the solubility. All right, are there any questions or comments here? All right, so that's an end to chapter 16. And now we will review a little bit today, and then on Friday, Monday, we'll take the exam. Okay, and then we'll start chapter 17 on Friday, right? All right, so this exam that you'll take on Monday has 11 problems. Okay. By the way, I have on page 6, I have a summary of all the acid-base equations, so it's worth taking a look at. Make sure you're good with these types of equations. What's a strong acid, what's a weak, strong base, and so on. All right, so just read over before you take the exam, study page 6 of your notes. But this exam will be about 9 problems and 2 short answers, true, false, that sort of thing. All right, so these are the type of problems that will appear on the exam. Now you have about 50 minutes to do it, so give yourself maybe 5 minutes a problem. Okay, the 2 short answers will take you, 10 seconds or so. All right, so the first problem is something like this. What is the pH of 0.025 molar phenol? And phenol is a weak acid. Okay, how do we know it's a weak acid? Because it's not one of the 6. Okay, so on the exam it will be not phenol but boric acid. Okay, but it's essentially the same thing. You're going to do the exact same thing. It's just a different acid, different weak acid, boric acid. So the way this works is you're going to write the equation. It's a weak acid. Okay, so the first thing you want to do is write the Ka for this. All right, what is the Ka? Okay, good. Okay, the Ka is 1 times 10 to the minus 10. That's a very weak acid, because 1 times 10 to the minus 10 is such a small number. And then we have, okay, you don't worry about the liquid here, 0.025, this is 0, this is 0. When you have a bottle of phenol, some of it will go this way, and this will be plus X and plus X. So this is going to be 0.025 minus X, plus X, and then plus X. Okay, we'll plug it into the equation here. So Ka is equal to the conjugate base. Okay, the conjugate base to this acid, and this is the base, and this is its conjugate acid. Right, so the Ka is 1 times 10 to the minus 10. Okay, this C6H5O minus is x, this H3O plus is x, this is 0.025 minus x, so x times x is x squared divided by 0.025 minus x. So here you can assume x is small, so 0.025 minus x is about 0.025. Okay. We call this the low ionization assumption. Alright, so that makes 1.0 times 10 to the minus 10 times 0.025. If I square root that, I will get x. Right, so what is x here? 1 times 10 to the minus 10 times 0.025. And let's square root that. I'm getting about 0.0000 bunch. I'm getting about 1.58 times 10 to the minus 6 molar. Okay, but that's x. But what does that x truly symbolize? Okay. Yes, this x is actually this, which is the concentration of the conjugate base. But to solve and get the answer to this problem, it's also the concentration of H3O plus. So pH is minus the log of the concentration of H3O plus minus the log of 1.58 times 10 to the minus 6. And what is that on our calculator? 5.80 is what I'm getting. So, as long as you get the process right, I'll just take half a point if your calculator is calculator error or something. All right. So that is the first question on the exam. It's very similar, but you'll get boric acid. Okay, boric acid. But you're going to do the exact same thing. Okay, we do this for a weak acid. All right, let's go on to the next part of this problem. All right, let's move on here. All right, I'm going to move on to strong acids and strong bases. Okay. So a pH of a bottle of 0.25 molar of HCl. Do we need the ice table here? Okay, so because HCl is a strong acid, you can just plug it in. Okay, so that should take you less than a minute, as long as you know that it's a strong acid. I'm getting a pH of about 0.60. Okay, does the pH have units? No. Okay, it's a scale and it has no units. How about this? Lithium hydroxide. Can I plug it in straight to the pH? Okay, so instead of calculating the pH first, what should we calculate? And is this a weak base or a strong base? So we'll plug that in here. I'm getting about 0.90, but this is not the answer. Okay, what is the answer? Okay, 13.10. Okay, a very basic pH. 0.60 is a very acidic pH because remember 7 is neutral. Let's move down here. pOH is 11. So what is the pH of this solution? Before we calculate the... Actually, we can calculate the pH. This is pretty simple. What is the pH? What is the pH? Okay, why is it 3? Yes, pH plus pOH is equal to 14. calculate the hydrogen ion concentration in this solution. Okay, so now we're going back. Remember I said we could go back and forth. So if pH is minus the log of the hydrogen ion concentration, get to go back and get the hydrogen ion concentration in moles over liter. It's going to be 10 to the minus pH, which is 10 to the minus 3.00. And you're going to do anti-log. Okay, see, anti-log, second log minus 3. So this is going back and forth between pH and the concentration of hydrogen ion. And it's 0.001 molar. Okay, concentration here is going to be molar. Right, calculate the hydroxide ion concentration in the solution. Okay, so here POH is 11. So if the POH is minus the log of OH minus, the OH minus is equal to 10 to minus POH, which is 10 to the minus 11. And what is that on our calculator? 1 times 10 to the minus 11. All right, I don't know if you know this relationship, but if you take the H plus concentration and multiply it by the OH minus concentration, you get Kw. And Kw is at 25 degrees 1 times 10 to the minus 14. So that's another way to solve this problem. Okay. Realize that H plus times OH minus is 1 times 10 to the minus 14, and then you solve for OH minus. So there's 2 ways to solve for this problem. One is utilizing this formula, or the other one just back calculating. Right, is this solution basic, acidic, or neutral? What do you guys think? pH 3? This is acidic. Okay. Anything of a pH below 7 is acidic. So here we're looking at a pH below 7 and a pOH above 7. Okay, this is what makes it acidic. All right, so that is these types of problems you'll see on Monday's test. Okay, we got three more pages here, so let's go to page 3. Alright, write the chemical equation Kb, not Ka, Kb. Okay, so we'll highlight that. Of the bicarbonate ion, identify the conjugate acid and the conjugate base in the chemical equation. Alright, so HCOO3 will react with water. This is Kb now. What does the B stand for? So we're going to make OH minus. All right, the way you make OH minus is that this proton is going to deliver this water. This water is going to deliver a proton, giving you H2CO3 plus OH minus. Okay, so this is Kb. Okay, conjugate acid. All right, so this is the base. What is its conjugate acid? What is the conjugate acid for OH minus? Okay, it's water. OH minus picked up a proton, becomes water. And what is the and this is the base because it took the proton. I'll put this in blue. And what is it? This conjugate acid? This is the acid. Okay, to this base. This is the acid to this base. H2CO3 became the acid because it picked up the proton. Okay. HCO3 minus took the proton. So if you take a proton, it becomes the base, and it becomes the acid. Okay. So these are pairs. Okay, these are pairs too. Yes. Yeah, do it like this. All right, instead of KB, we'll do KA now. What does the A stand for? Acid, so we're going to make H+. Actually, we're going to make H3O+. All right, so we start with formic acid plus water. Okay, this is going to give us now, this is the acid. Compare this with this. This is the acid. Okay, what do acids do? They're givers. Very good. What are bases, Royce? They are takers. You read my mind. Takers. Okay. And then, remember, this is Ka now. So what are we getting? Hydromonium ion, and then HCOO minus. Alright, so this would be Ka, and we'll do the same thing now. Formic acid is obviously the acid. What is its conjugate base? This is called formate. That's not something you need to know, but it's called formate. And water is taking the proton, so this is the conjugate base. What is its pair? The conjugate acid is this. Okay. Right, so just compare these two, study these two. One of them is the equation that typifies a Kb for a weak base. This equation typifies Ka for a weak acid. All right. Any questions or comments here? All right, so you'll get a different base here, you'll get a different acid here, but you know the idea is just the same. I'm going to move on. Excuse me. All right, ranking acids here. All right, so pKa, that lowercase p stands for power. Okay, power. So pKa is equal to minus the log of Ka. So let's quickly minus the log these guys. Okay, so let's do that fast. Minus the log of 7.2 times 10 to the minus 4. 3.14 minus the log of 1.9 times 10 to the minus 5. 4.72 minus the log of 0.16. Okay, this is what you'll have to do. 0.79, yeah, 0.80. Minus the log of 3.5 times 10 to the minus h. Uh, 7.45 is what I'm getting. So can we do this on our calculator for the exam? You know how to do this? Minus the log and then minus the log of the Ka. 6.2 times 10 to the minus 10. I'm getting 9.21. Okay, and then finally, HNO2, nitrous acid, is 4.0 times 10 to the minus 4. Ugh. 3.40. 3.39, 3.40. All right, the least acidic to the most acidic. So we'll call the least acidic 1, and then the most acidic 1, 2, 3, 4, 6. Okay, so how will we rank these? Okay, so the lower the pKa corresponds to higher Ka. And this is what we mean by something that's acidic. Okay, so you can look at the highest Ka value, or you can look at the lowest pKa value, and that is the most acidic. So which is the most acidic here? I'll call that 6, right? Just be careful, because my brain also kind of goes backwards. So 6. And then what's the next highest? This? 5. Okay, then what's the next? 4. 3, just double check. 2, am I right? 1. I go back. My mind can't go back and forward and backward. Is this correct? 10 to the minus 10 is the least acidic. And then that's, yeah, so just, yeah. Well, do you guys understand this, the ranking system? Okay, so I'm going to rank it, the lowest pKa is the least acidic. Or the highest pK, the highest pKa. Highest pK. So 1, 2, 3, 4, 5, 6. I think that's right. Okay. All right. Is everyone okay with this? Okay, understand this? Okay. This is how the ranking goes. So 6 different acids. Each acid has different propensity or different strength. Okay. The strength is based on this relationship. All right. So let's go now to this type of problem here. Calculate the pH of a solution made by adding 35 mLs of formic acid with 30 mL of OH minus. All right, so when you add formic acid, HCOOH, we're going to call that a weak acid. We will call NaOH, which is the source of OH minus, the strong base. So this is the reaction that happens. Okay, this is a strong base, so it's going to take that proton as much as it can and give you formate. Formate is the conjugate base. All right, let's figure out the concentrations after mixing. All right, we'll first do OH minus. And 30 mL of 0.10 molar. And what's our total volume? Are you guys getting 65? Yeah. So what's 30 times 0.1? 30 times 0.1 is 3. Divided by 65. I'm getting 0.0462 molar. Okay, mils and mils cancel. Okay, let's figure out the concentration of the weak acid. Okay, this is the concentration after mixing. Okay, this is going to be 35 mLs times 0.1 molar. What's our total volume? Okay, as Sam said, it's 65 mLs. The mils and mils cancel, so 35 times 0.1 is 3.5. Divided by 65. 0.1 molar. One, two, three, four. Which one? 0.01? Hold on. 35 times 0.10. 3.5 divided by 65. 0.05. Oh, I'm sorry. Okay, thank you. 0.0538. All right, thank you. You know, I did that on purpose to see if you could catch me or not. And you did. All right, how much of the strong base will take up this weak acid? All of it, and all of it is, yes, 0.0462, 0.0462 plus 0.0462. Let's see here. I think I have to give you the Ka for formic acid, but I don't have that in front of me. But anyways, so what's 0.0538 minus 0.0462? 0.0076 molar. That's 0. Going to be 0.0462. Okay, so here you have HCOOH, you have HCOO minus, so we'll use the Henderson-Hasselbalch equation with the Ka of formic acid, which I don't know off the top of my head. Let me see if I can find it. So I'll give you that on the exam. Ka of formic acid. Let me just find that. Do you guys know the Henderson-Hasselbalch equation? Okay, I'll give that on the test, so that's okay. But the Henderson-Hasselbalch equation is pH is equal to pKa plus the log. Okay, you're going to drop the acid, and that's going to be HCOOH divided by HCOO minus. All right, so pKa is minus the log of Ka. So let me give you the Ka of formic acid really quickly here. And it is 1.78 times 10 to the minus 4. Okay, that is the Ka for formic acid. So minus the log of 1.78 times 10 to the minus 4. Okay, plus the log of 0.0076, okay, and then HCOO minus is 0.0462. Okay, can we do this on our calculator? Okay, I'll give you this equation. This is the equation we'll use because you have HCOOH and you have HCOO minus, so that's a buffer. Plug it into the Henderson-Hasselbalch equation, and first we'll do this fraction, log it. So 0.0462 divided by 0.0076 log that. I'm getting 0.784. Okay. And what's minus the log of 1.78 times 10 to the minus 4? Minus log 1.78 times 10 to the minus 4. 3.75. So 3.75 plus 0.784 gives us the final answer, 4.53. Alright, so that is the pH. So the key here is that when you have some of this, which is the acid, and some of this, which is the conjugate base, you can use the Henderson-Hasselbalch equation, which is shown here. Okay, I'll give you this equation on the exam. Is everybody comfortable doing this type of problem? Okay, on Monday? Let's see the time here. Alright, we've got 5 more minutes here. Write the KSP expression for silver 1-phosphate. Silver 1-phosphate. Alright, so silver 1-phosphate is this. Alright, the KSP. Okay, that means it's a solubility product constant. So we will take Ag3PO4. Okay, this is what you want to write on the exam. Ag plus PO4 minus 3. Okay, I'm also going to grade for the states. Okay, a lot of students won't put the solid and won't put the aqueous. I'll subtract half a point. Okay, because this is in essence what a solubility product is. Solid going back to its ions. What's another thing we need to do in all equations? Every equation, what needs to be done? Balance. So to balance this, you get that. Okay, so you can write the equation and then the expression. This is the answer actually. KSP is equal to Ag plus. Okay, what should I do with that Ag plus? Qubit times PO4 minus 3. Okay, so on the exam you want to report these two and you got to put the states in. Okay, if you want full credit, because this is the right way to do it, you have to put the states. So a solid going back into aqueous. Let's see how we're doing on time. We got 3 more minutes and we have 1 more page left. Let's see if we can do that. Okay. All right, the solubility of silver carbonate in the presence of 0.1 molar sodium carbonate. So this is just like the one we did before, except we have what we are going to call the common ion. Okay. And they tell us the KSP here is 8.10 times 10 to the minus 12. So some of it will go here back, and that's going to be S. Okay, but we have here a common ion. What's our common ion? Okay, CO3 minus 2 is our common ion. So some of the Ag plus will go back. That will give us S. Some of the Ag2CO3 will go back to give us SHG plus and SCO3 minus 2 plus what else? The common ion. Okay. So what's the common ion here? CO3 minus 2. So we'll plug that into our KSP. What do we need to do here? So it's squared times CO3 minus 2. Okay, this becomes S squared times S plus 0.10 equals KSP, which is given to us in the problem as 8.1 times 10 to the minus 12. Okay. All right, so we assume S is small. So that's going to be 8.1 times 10 to the minus 12 equals S squared times 0.10. Okay, so we're assuming most of the S that goes this way is S, but most of the carbonate that goes this way comes from the common ion. Not just S, but most of it comes from 0.10 sodium carbonate. So we'll just solve for S here, and that will be the answer. Okay, so that will be our solubility. And what is that? Quickly on our calculator so we can solve this one here. .00, 9 times 10 to the minus 6. Okay, and then I will take off points if you don't have the units. Okay, half a point. Okay, here the units are molarity, molar. So the solubility of Ag plus is going to, oh, I made a mistake here. Okay, maybe we'll have to do this again Monday. Okay, this is plus 2S. Okay, so 2S squared is 4S squared, so this actually gets divided by 4. Okay, do you see that here? Okay. 2S squared. Okay. It became 0.1 because S is small. Yeah, so this becomes 4S squared over times 0.10. 4S squared. So anyways, yeah, it's actually 8.1 times 10 to the minus 12 divided by 2 squared. So this is 4S squared, so it becomes divided by 0.4. Okay. All right, so we'll do this again tomorrow, or I'm sorry, on Friday. Divided by 0.4. Okay, and then square root of that. Okay, the correct answer is 1.8. Okay, 1.8 times 10 to the minus 6. Okay. Okay, so the solubility of Ag plus will be 2 times that. And that's going to be 3.6 times 10 to the minus 6 molar. Okay. So basically, you're going to put your 2s in here. That becomes 2s whole squared. 2s whole squared is 4s squared. Okay, 4s squared. So the 4 goes down here. Okay, I got to go. It's very late. And we will see you all and complete this on Friday. Yes, I'll post it. I'll scan it and post it on Canvas.